We're going to look at how to write very large numbers in maths, looking for an easy way to write very large numbers. And I'm going to start off with a number that's not too large, but we'll use that to look at the process, and then we'll move into some much bigger numbers after that. So let's consider 8,000. 8,000s, 8 is in our thousands column, and we have nothing in our hundreds, tens, or units. So essentially what we've got there is 8 thousands, or 8 multiplied by 1,000. Okay, now that's a really quite a simple move, but it's a really important one, because what we've done is we've separated out two factors here. We've separated out our 8, and this one here we've separated into a nice neat power of 10. We know from what we did in a previous video that 1,000 equals 10 times by 10 times by 10. So what we've got here is 8 times by 10 times by 10 times by 10. And another way of writing 10 times by 10 times by 10, of course, is 10 to the power of 3. So what we've actually got is 8 multiplied by 10 to the power of 3. That means 8,000. And this is called standard form or scientific notation. And it's particularly useful when we go on to look at much, much larger numbers. So let's have a look at a bigger number. Let's say we had 2,400,000. Okay. So using exactly the same process here, if we were to separate out our number at the start, before we just start putting these zeros in, what did we have? Well, we've got 24 multiplied by a number which is all of these zeros. So that's 24 multiplied by 100,000. Interestingly, again, we can, 100,000 we know is 10 times by 10, which is 100, times by 10, 1,000, times by 10, 10,000, times by 10 again, 100,000. And if we look at these tens at the end, we've got 10 times 10 times 10 times 10 times 10. Well, that is 10 to the power of 5. So our number is 24 times by 10 to the power of 5. Now, interestingly, a decision was made that for standard form or standard index form, or scientific notation as it's also called, that this number at the start would always be less than 10. So as we've got here, 8 times by 10 to the 3, this is less than 10. But we've gone over 10 here. We've got 2 in the tens column. So how can we make this number less than 10? The way we would do that is to essentially divide this number by 10 to give us 2.4, satisfying that condition that our start number is less than 10. But if I was to just write 5 in here again, well, of course, these are different numbers now. 24 times 10 to the power of 5 is bigger than 2.4 times 10 to the power of 5. So because I've divided this part of our number by 10, I'm going to multiply this part of our number by 10, so that overall the entire number is unchanged. So 10 to the 5, which was 10 times 10 times 10 times 10 times 10, we're going to multiply that by another 10, we get 10 to the 6. So 2.4 times by 10 to the 6 is the same way as writing 2,400,000. Okay. Let's see if we can find a quick way of doing this. Let's take another example. 300 347 million. So remember, for standard form, scientific notation, what we're looking for is a number times by 10 to the power of something. And the number that we're going to start with has got to be less than 10. So 347, well, that's not less than 10, so we're not going to start with 347. Supposing we brought a decimal point in here, 34.7, it's not less than 10. Okay, so supposing we brought a decimal point in here, and that would make 3.47. All we've done is bring our digits across so that our decimal point ends up here, actually 3.47. So we need, what would we need to multiply 3.47 by in order to make 347 million? We're going to multiply it by 10 to the power of something. 347 million. If we were to just focus on this 3 and think, how many places would I have to move this 3 in order to bring it to the position I want, which is here, just in front of the decimal point, the units column? Well, let's have a look. It's got to move 1, 2, 3, 4, 5, 6, 7, 8. So 3.47 times 10 to the power of 8. And that's how we put very large numbers into scientific notation.
Okay, Mary, so let's have a look at this one. So solve x plus 2x equals 12. So what do you think you do first?
Okay, well, I want x on its own, so I would put x equals 12 minus 2x.
Okay, so a lot of the time we want to get x by itself, but what we want to do first is get all of these x's together. So can you see anything we can do with this? Get all these together in one place.
Oh, okay, it's 3x, isn't it?
Yeah,
so
absolutely.
3x equals 12. Oh, and so x equals 4.
Brilliant, spot on, well done.